Data detection framework for spatio-temporal data mining. Abstract. With the unpredictable increase in the generation and use of spatio-temporal data sets, the efficient handling of large volumes of spatio-temporal sets has been the subject of many research efforts. With the phenomenal growth of computer technology everywhere, mining from the enormous amount of spatio-temporal data sets is seen as a central technology that can provide information for real-world applications. Big spatial data apps cover a wide variety of interests, including infectious disease monitoring, simulation of climate change, opioid addiction, and others. As a result, significant research efforts are carried out within these applications to facilitate efficient analysis and intelligence by either offering spatial extensions to existing machine learning solutions or designing new solutions from scratch. Based on the concepts of states and events, the conceptual model was developed, and the use of time as a basis for organizing spatial data allowed the time and place of any modifications to be recorded. This paper proposes a conceptual-level spatio-temporal modeling approach, called MADS. The idea results from the description of the conditions for a conceptual model to be fulfilled. We can easily formalize spatio-temporal data mining challenges using the proposed knowledge discovery system. Keywords: spatio-temporal data mining, discovery of spatio-temporal information, spatio-temporal moving pattern, system for discovery. 1. Introduction. Different technologies for ubiquitous computing and services have been developed in recent times, with wireless sensor networks, context awareness and open service architecture now considered as the core elements of these programs. The ubiquitous service infrastructure is now being realized, in which we can access desired information and services at any time in any area. Most services have a close interaction with real-world artifacts, events, and changes. As such, spatio-temporal information and knowledge are generally required by the services. Many research efforts have been focused on the efficient handling of the large volume of these datasets with the explosive rise in the generation and usage of spatio-temporal datasets. Spatio-temporal sequences. However, there are many difficulties in extracting as well as handling knowledge because of the sophistication and enormity of spatio-temporal information. The real-time, high-performance and continuous extraction of information from large-scale spatio-temporal datasets is needed to provide more intelligent services. Spatio-temporal data mining poses several difficult research problems with regard to the extraction of useful spatio-temporal information from large spatio-temporal datasets. For example, ubiquitous services such as telematics, location-based services, surveillance apps, and real-time environment monitoring applications, for example, all require the handling of a large amount of spatio-temporal datasets, but also the promotion of useful information for decision-making in real time. Centered on current techniques for temporal data mining. From the spatio-temporal data collection, we can discover spatial or temporal knowledge or spatial data mining techniques for. However, by considering both the temporal and the spatial elements of objects, new forms of spatio-temporal information for services can be extracted. 1, 6, 7. It is important to endorse a new paradigm for this sort of discovery. First, the discovery question should be more formally specified by any new paradigm for spatio-temporal data mining. In this paper, after considering the several spatio-temporal models previously proposed, we propose a new foundation model for information discovery. Second, based on available and useful spatio-temporal operations and topological relationships, the development of new mining techniques should be encouraged. Given the remarkable growth of ubiquitous computer technology, mining from the enormous amount of spatio-temporal datasets could become a central technology that can provide information for real-world applications. This paper's description is as follows. We study a number of previous research efforts in Section 2 related to the exploration of spatio-temporal information and discuss some of the problems. In Section 3, we suggest a 3-tier spatio-temporal information discovery system, and in Section 4, as a base model of the system, we define the spatio-temporal information model. In the 5th segment, the implementation model, which includes a description of the problem and the design of the framework of spatio-temporal discovery of information, is defined. 2 criteria and related work. In the literature, most comparisons of spatio-temporal models usually seek to determine the consistency of a model with regard to its competitors. Therefore, from one article to the next, claims and conclusions differ. There are also a few more general parallels. See, for example, the study of object-oriented temporal languages in 24. Significant work is recorded in 12,13, which analyzes and classifies 10 temporal entity relationship models according to 19 design criteria. Most of these conditions are peculiar to the temporal dimension. We are interested in the more general question, what characterizes a strong spatio-temporal database conceptual model? Many well-known responses come from previous experience in the design of traditional databases. For example, the word conceptual refers to the ability to provide a clear mapping, i.e. without distortion, between the real world perceived and its representation. In the proposed spatio-temporal models, examples of distortions involve excessive constraints due to weak data structuring capabilities, e.g. binary relationships only. No attributes with multivalued values. Many models, e.g., GOOM25 and Pollen 11, reflect spatial or temporal characteristics of object types across space or time, e.g., point, line, instant, time interval. In computational modeling, such artificial object types do not represent real-world objects of interest, thus contradicting the very first law. The model has to have strong structures to prevent distortion. Support for entity types, relationship types, multivalued attributes, complex attributes, i.e. attributes composed of other attributes, is a links, aggregation, part of, links, and related integrity constraints is the current norm in this regard, as represented by, e.g., UML4. Many more characteristics can be considered, but experience has shown that aiming for the highest expressive power contributes to intolerable difficulty and inevitably results in rejection. The model. Also, users are likely to discard models with too sophisticated constructs or with constructs having non-standard semantics. The next important criterion, therefore, is simplicity, which also applies to the visual notations that support schema diagram drawing. Some versions do not contain visual notes 5, 11, 18, 25, whereas others do not contain intuitive notes 10. Of course, a conceptual model should rely on a sound, formal description, and there is a lack of such a sound context in some proposals. Finally, for both data definition and manipulation, an associated data manipulation language would allow the use of the same model. How the dimensions of space and time are applied to the model is the latest, fundamental problem of spatio-temporal models. The only correct criterion is, in our view, orthogonality. This idea refers to the independence required between the dimensions of modeling, data structures, space, and time. Database designers should be able to decide the most suitable data structures for an application, without taking into consideration which spatial or temporal information objects carry information. Once the data structure is fixed, if necessary, space and time features can be freely added. This approach also makes it easier to incorporate space or time characteristics to legacy databases that do not normally contain unique spatio-temporal requirements. Most of the existing spatial models lack orthogonality, requiring the designer to provide spatial information with a particular representation. GOOM 25, Pollen 11, Modular 2, and Congu 19, for example, are only support the connection of object types with space. An object type may therefore not include attributes that represent spatial information, such as the reservoir attribute in the Figure 3 example. GO25, on the other hand, does not have any definition of a spatial object, only attributes can be spatial. It is not possible to decide which object type, if any, represents the spatiality of the objects, from the description of an object type with many spatial attributes, e.g., watershed in Figure 3. Likewise, not every temporal model advocates the correlation of time with artifacts, experiences, and characteristics. In endorsing temporal entity types, for example 14 lacks the facilities provided with redefinition by conventional inheritance, thereby demonstrating another way of not achieving orthogonality. Beyond orthogonality, model simplicity, as well as ease of use and comprehension, is greatly improved if the modeling of spatial and temporal characteristics relies on similar contexts of reasoning. The comprehensiveness of a spatio-temporal model is another concern, i.e. how many of the perceived phenomena of space and time should be explicitly capable of representation in the model. This includes problems such as supporting spatiality dimensions of 2.5 or 3 or supporting temporality valid time or transaction time. Without coming to a consensus, several such topics can be debated. The more, as already suggested, is not always the best. Extensible models look like the best answer, but it is not an easy task to determine a model's extensibility. Again, orthogonality proves to be an important quality because the effect of introducing a new idea to the model is restricted by having orthogonal dimensions. However, there is a point we want to emphasize in terms of comprehensiveness. Since we agree that conceptual models should endorse objects, relationships, and attributes directly, and we want to include spatio-temporal objects, spatio-temporal relationships, and spatio-temporal attributes since we firmly insist on orthogonality. Present plans lack spatio-temporal relationship support. These relationships have been ignored, depending on the underlying GIs to measure the individual relationships. Mostly topological, from the coordinates of objects stored in the database. An obvious downside of such an approach is that a spatial relationship cannot be added to any property. In conclusion, none of the spatial and temporal models we have studied satisfies any of the above objectives, which contradicts the expressive capacity required in the structural dimension. This prompted the creation of MADS, a conceptual model for object relationship. MADS's main originality lies in the fact that it is a conceptual model indeed. Still, it has been introduced by translating MADS specifications into usable database models by translators. For example, in 20, a mapping of MADS temporal constructs to TSQL223 was defined. For conventional land management applications, the MADS model currently covers requirements, 1 or 2-dimensional spatial data, priority for discrete object view versus continuous field view, valid time only. Present work on MADS requires an expansion to multi-scale databases and transaction time. 3. A spatio-temporal knowledge discovery framework. Fig 1 Knowledge Discovery Framework. A structure is referred to as the collection of principles, models, and methodology essential for the exploration of knowledge. As shown in Fig 1. Our architecture consists of 2 models, a model of the foundation and a model of implementation. Here, the foundation model refers to a 3-tier model of spatio-temporal knowledge, which is intended to describe a collection of spatio-temporal objects as well as a volume of knowledge. A spatio-temporal data layer, a spatio-temporal information layer and a spatio-temporal comprehension layer are included in the conceptual spatio-temporal knowledge model. The representation of data and information, the algebraic operation on spatio-temporal objects and the representation of the knowledge extracted are supported by this model. The spatio-temporal knowledge discovery model, as an implementation model, involves the concept of spatio-temporal information and knowledge evolution and the method of discovery of spatio-temporal knowledge. We suggest an architecture for the spatio-temporal method of information discovery in order to validate our knowledge discovery model. 5 interrelated layers compose the proposed device architecture, a data layer, an information layer, a spatio-temporal mining layer, a knowledge layer and an application layer. 4. A conceptual 3-tier spatio-temporal knowledge model. First of all, to derive useful knowledge the requisite properties of the foundation model over the spatio-temporal phenomenon are as follows. Firstly, the identity and presence of spatio-temporal phenomena must be properly explained. Secondly, the representation of phenomena must be capable of being represented. Thus, not only must the static and dynamic elements of spatio-temporal objects be included, but the temporal element, the spatial element and the attributes must also be considered as the 3 main elements of the object. Third, for the study of phenomena, it must be capable of reflecting multilevel context information. Finally, it must be able to use previous experience to mine new forms of knowledge. Among the current knowledge models, we chose the pyramid model of Manus 5 as the most fitting model of spatio-temporal knowledge and developed it to meet our own requirements. The computational knowledge model proposed for the replication of spatio-temporal phenomena actually reflects the spatio-temporal data observed, the spatio-temporal information analyzed, and the spatio-temporal knowledge discovered. As shown in Fig 2. In this model, the data portion consists of representations of the spatio-temporal data occurring in the spatio-temporal universe. In order to extract the value, the information component concerns the selected end. Meaningful data extracted from the data component by using a generalization or transformation operation. Finally, the aspect of knowledge describes objects of knowledge which are useful to human beings. Awareness may be explicitly induced or implicitly induced from spatio-temporal information or a priori awareness from a collection of spatio-temporal items. Our conceptual knowledge model for representing spatio-temporal phenomena, focused on the idea of a value chain and conceptualization, clearly represents the spatio-temporal data observed, the spatio-temporal information processed, and the spatio-temporal knowledge discovered. Compared to Mani's 2-tier data component and knowledge model, our model is able to abstract the various operations performed on the spatio-temporal data set by providing an information component. The abstraction of spatio-temporal activities makes it possible for the current legacy DBMS systems such as relational DBMS and/or DBMS to incorporate the information discovery framework. 5. Spatio-temporal knowledge discovery model. Definition of spatio-temporal knowledge. To better represent the spatio-temporal information mentioned above, it is important to include a method of representing temporal qualifications in the temporal domain. A more complete description of the time expression of temporal information has been given by Li Tu, including the time expression defined by Chen. The calendar interval expression set is denoted as cis for each time expression set, the calendar relationship expression set is CRS, the time interval expression set is TIS, and the periodical time expression set is cis. PTS as well. Let TQ time expo be the temporal qualification, where time expo equals cis, TIS, PTS. In addition, the manner in which the spatial qualification of the spatial domain is interpreted has to be given. The spatial qualification SQ of knowledge applies to the spatial domain ES, where it refers to a valid spatial domain coverage of knowledge. A primitive RP of spatio-temporal information is an indivisible information unit with a temporal qualification, as well as a spatial qualification along with a definition of the law. Since primitive spatio-temporal knowledge can be expanded by adding temporal and spatial qualifications from the existing definitions of the law, knowledge can be described as follows. Let primitive RP be spatio-temporal information rule, TQ, SQ. Now, this concept will redefine existing forms of information, such as descriptive information, temporal knowledge, and spatial knowledge. Spatio-temporal knowledge R is defined as a compound of the primitives of spatio-temporal knowledge and as follows. The unique identifier RID. R equals RID, RI plus, where RI plus, where RI RP. As a set of information discovered, i.e. RI. R, a spatio-temporal information set R is specified. In the timeline T, information was located at a time point T. A new spatio-temporal information snapshot set is created whenever a discovery occurs. Spatio-temporal knowledge discovery. The discovery of spatio-temporal knowledge consists of the discovery of a spatio-temporal knowledge set from the spatio-temporal data set given. It should also be possible for spatio-temporal awareness to link space and time with object and relationship types in order to convey an intrinsic spatiality or temporality that does not depend on their semantic attributes. A predefined feature, geometry, MATS, allows object and relationship instances to be suspended and resumed in their membership to describe the spatiality of an object or relationship form. The status attribute therefore differs in time. It is a time-to-status function, where status is a predefined domain consisting of 4 values, non-existent, active, suspended, and disabled. The first value relates to an object that is believed to exist sometime later. An object that can be used within the associated time frame is defined by the active value. It is possible to read but not change the properties of suspended objects. Finally, the disabled attribute identifies an object that has existed in the past but is not available during the disabled timeframe 9. The following restrictions apply to transformations between values: not yet existing active, active suspended, active disabled, and suspended disabled. Status-related features include the life cycle, the birth-to-death interval, and the active cycle, the active status-related set of intervals/instance. 6. Spatio-temporal knowledge discovery. The discovery of spatio-temporal knowledge consists of the discovery of a spatio-temporal knowledge set from the spatio-temporal data set given. The problem of extracting the spatio-temporal information set Rs from all information R equals RID, RI plus that meets the given thresholds from the given spatio-temporal data set DS, using the context knowledge provided, is known as a spatio-temporal knowledge discovery. 2 flows are composed of the proposed information discovery process model. In other words, the development of a mining method and the discovery of spatio-temporal information. The creation of the discovery objective, data discovery, a summary of the discovery profile, and the development of a mining operation are the key development processes of information discovery techniques. Information discovery processes consist of 5 steps: task creation, specific data set creation, spatio-temporal data mining, visualization, and analysis and assessment. The key components and their relationships are represented within our implementation model. Entry to the heterogeneous spatio-temporal data set helps the spatio-temporal data and knowledge layer. In this layer, the permission request is mapped to the physical access of each storage from the higher layer. The spatio-temporal mining layer performs the extraction and transformation of data, and then uses spatio-temporal mining operators to discover rules. Therefore, in this layer, access to the lower layer must be supported. Both the application layer and the mining layer are connected with the information layer. Novel features such as the representation of rules, the access and preservation of valid rules, and the translation of the rules to applications are included in this layer. Implementation and discussion. Implementation of a spatio-temporal knowledge discovery system. To demonstrate how the proposed structure can be extended to the creation of a system for the discovery of spatio-temporal information, we briefly define the system for the discovery of spatio-temporal moving patterns, i.e. Mpminer, which is implemented based on the proposed architecture as a semi-tightly coupled structure. As mentioned above, the 5 layers in the framework's implementation model correspond to the framework's 3-layered conceptual spatio-temporal information model. These major modules consist of the framework. As seen from Fig 4, Mpminer is a method of moving pattern discovery that includes the mpmine operation as the main mining operation and is introduced as a semi-tightly coupled structure. Via an extension of the DBMS procedure and the implementation of the information and knowledge portion of the proposed architecture, this structure has the advantages of successful data processing. Fig 4. Implementation of Mpminer. The implementation of this scheme is split into the implementation of the system and the execution of the UI and mining activities. The implementation of the system corresponds to the implementation of the conceptual model of the 3 elements. The data portion is implemented using Oracle AI as a set of relationships. Just in Fig 4, contains the MD data collection of moving objects and the chart of context map data. The main relational algebra activities are expressed as SQL, as the knowledge portion. Using PL/SQL, spatial and temporal operations are represented as the stored procedure. It contains the time expo function for time expression processing and the SC generalize function. The knowledge portion is implemented as a set of relations in Oracle AI in order to represent the discovered knowledge and context knowledge. HG trees are often implemented as a collection of connections by normalization to represent a spatial conceptual hierarchy. Also, the spatio-temporal moving patterns discovered are stored as a relationship. Discussion. As a result of the assessment, the proposed paradigm provides the proper representation of the spatio-temporal phenomena for knowledge discovery by providing a foundation model that is based on the event-based model and that hierarchically represents the 3 related components such as data, information, and knowledge. Some concerns still occur, however, where data limitations and confidentiality are not taken into account. The system supports forms of multiple knowledge with regard to context knowledge, such as temporal knowledge, spatial knowledge, and spatio-temporal knowledge, as well as user-defined knowledge. The method of representing knowledge, however, and the kinds of knowledge operations are still to be included. It promotes integrated information exploration with regard to the support of knowledge discovery integrated with the already knowledge-minded. Maintaining knowledge and the evolution of knowledge, however, has not been properly considered. Finally, even operation abstraction is possible with regard to implementation in the legacy system, although in some legacy systems it is limited. The system needs to be strengthened in the future by considering the concerns that have been found. 7. Conclusion. The emergence of ubiquitous computing, the development of wireless sensor network technology, and the growing need for context-aware services and intellectualization have led to increased understanding of the enormous volume of spatio-temporal data and the study of information discovery. Many of the new services strive to provide consumers with more customized and intelligent features. Real-time, high-performance, and continuous extraction of information from the enormous amount of spatio-temporal datasets is required to provide more bright services. In this paper, we discuss a structure for the exploration of spatio-temporal information that encourages the creation of new types of knowledge, such as the pattern of spatio-temporal movement. The meaning and relationships of spatio-temporal datasets and information can be interpreted in the proposed system by using a foundation model for knowledge discovery. In addition, the concepts of spatio-temporal knowledge and knowledge discovery processes and models there are some merits to the spatio-temporal information exploration paradigm discussed here. However, given the characteristics of the spatio-temporal datasets of recent applications, the size of the datasets is growing because of the continuously evolving spatio-temporal artifacts, because of the convergence of services, the need for real-time analysis has increased, and the semantics of derived information are becoming more complicated.